So, hi everyone. So today what I want to do is to explain 2 points that make the KAM scheme is a little bit more different or difficult than regular iteration scheme for convergence. Okay? So in another video I showed, right, or I explained a little bit that if one starts with a Hamiltonian of this form, okay, where this term is small, okay, and omega, okay, is the open time. Okay, what we would like to have is that this term didn't exist, so this Hamiltonian is the one that describes the dynamics. Okay, so let me reformulate this statement. What we want is, okay, what we want is in general, is that if we have that the Hamiltonian is of this form, okay, where this is small, and this term looks like this one, okay, so h of p, okay, h of p is of the form this plus quadratic plus something else, okay? And then what we want is that we can perform a change of coordinates that is Hamiltonian, okay? We would like to prove that there is a change of coordinates such that the Hamiltonian transforms into a Hamiltonian of this form where h hat is like this. Okay? Very good. So we want to move from this Hamiltonian to this Hamiltonian. The other day we saw that from this Hamiltonian where this is small, we can perform a change of coordinates, and this change of coordinates was given by the flow, okay, by the Hamiltonian flow of a function that we're looking for, okay? So we're looking for a function f such that it acts as a Hamiltonian, and then this has this flow, okay? Then what we saw is that we can choose f and then get a new Hamiltonian by composing our previous Hamiltonian with this flow, such that, okay, where this is small square, okay, and we couldn't get rid of the average of G. Okay, recall that when we were solving, so we were solving a small divisors equation, and we couldn't get rid of this. We were solving an equation of this form. Okay? And then we saw that we can find f that satisfies this linear PD as long as this one has average 0. So what we do is that we take the average and join it into here, but it doesn't affect that much because notice that this is small, and what we get is that we started with this beautiful Hamiltonian, and we get a new Hamiltonian that only depends on this, on the action. Okay? So in general, when thinking about the scheme, what one wants to do is something like h of pq, start with h of p plus g of pq, and then this moves to a new Hamiltonian, that this new Hamiltonian is produced by composing under a suitable flow map with a suitable f, that is h nu of p plus g nu of p here. Okay? And we want that g nu, okay, is of size the g of square. Okay? And also h minus h nu, okay? We also need to control the distance between our old h and the new h. This is of size. Of size g. Okay? So that's how we perform a KAM scheme. We start with Hamiltonian, and then we get a new Hamiltonian such that the desirable part is very close to the old one, and what we want to get rid of, we cannot get rid of, but we obtain something that is of size of this size. Okay? Very good. So then there are two ingredients when one performs KAM. There are two ingredients. There are two ingredients that make things more difficult if we compare it with a standard fixed point here. Fixed point argument. Okay? One ingredient. Okay? So these are, I call them two ingredients, but more or less, yeah. So one ingredient is the following. So when one solves this equation, okay? When one solves this equation, we have omega d of attelle. Okay, so omega satisfies this, there is gamma tau. X is gamma, okay, d of attelle gamma tau. Then what happens is that, so we wonder, what is the size of f with respect to the size of g? Okay? Or, yeah, is this linear operator invertible? And the question is, and the answer is, it is not invertible. Okay? What happens is that if we take the norm, the analytic norm, in a complex string. Okay, this means that, so that's the torus, okay, and this is the torus plus a rho, Okay, I'm drawing the one-dimensional, but it's the same. Then we take the max norm at the boundary, because it's the max norm inside, because these are analytic functions. Then what we have is that, so if we have G, okay, and we evaluate it, okay, and we get the norm at the band rho, then the norm of F, we need to pay a price, pay a delta price, so we need to diminish a little bit the band with delta, and then what we have is that now we can compare this norm with this one, and this is by a constant, okay, an explicit constant that now is not very interesting, gamma delta lambda. Okay, this inequality is a very famous inequality in KAM, and it's by Rossmann. Okay, Rossmann studied this inequality, and this is called the Rossmann inequality, most of it. And then there is this explicit constant. Okay, you can get upper bounds of this constant, and you can get better or worse upper bounds. Doesn't matter too much. Okay, so that's one ingredient. So what happens is that every time that we perform a step, okay, we had G, and the new G, okay, we need to shrink, okay, with delta, because the new G depends on F, and F, we can only control it in rho minus delta, okay? So in fact, we have things like this, and the same will happen here, okay? Well, not the same, but mostly the same. Okay? So that's one ingredient. Okay, and then another ingredient which is not that painful, but it also happens to have this, is that means something very similar, is that when one does h du, that is h composed by phi, because phi depends on F, and F is only controlling rho minus delta, then h nu is also only controlling rho minus delta. Okay, so the new Hamiltonian is this. So what happens? Okay, so this ingredient makes the following obstacle. So you start with your data, initial data, okay, and you have to control it at a rho, okay, h initial, okay, you control it at rho, but then let's call it h0, but then, okay, so we have this, and then we obtain bounds for h1, so we need to subtract a delta. Which delta do we subtract? Well, let's say a delta. But then, what we cannot do is then start subtracting always the same delta. Because if we do this, we can only do this finite number of steps. Okay? So instead of doing this finite number of steps, what we want to do is to subtract less and less and less and less and less delta. Okay? So what we want to do is something like, if we started at rho, then we subtract a delta, then the next one we will control a rho minus delta, that was the previous one, minus delta squared, then the next one delta squared, delta cube, okay? So we can choose to do a geometric series. Okay? And then now we have the hope that this converges, because the geometric series is 1 minus 1 delta minus 1, right? That is delta divided by 1 minus delta. Okay, so if we choose that we remove at each step just delta, delta squared, delta cubed, delta 4, and so, then at the end we will have, right? The final data will be controlled up here, and as long as we choose delta such that this is smaller and such that this is positive, then the final data is still analytic. So which assures us that at all steps the data is controlled. But what is the problem? What is the price that we are paying for doing this? The price that we are doing for this, the price that we are doing for this, the price that we are paying for this is that every bond, okay, we want to prove, okay, that the idea of the goal is that we go from good plus bad to the new, which is the good one and the bad one. Okay, and recall that these ones are always okay, squared of the previous one. But these ones, okay, they come from solving this equation. Okay, modulus equation. And when we were solving this equation, we had, okay, the Rootman inequality. We have constant, but this constant is global for everyone, gamma delta delta. Okay, so the price that we are doing is that, yes, this is something like this, but then we have these divisions. Okay, so we have divisions like this. So delta goes to 0, okay, because we are forced to do delta goes to 0, so we at the end retain the scheme. So at the end we retain that we have an analytic function, but at each step delta diminishes geometrically, right? So this blows up. The beauty in KAM, okay, the magic in KAM is that although delta goes to 0, so constant blow up, we end up having that the knowns of the GKs goes to 0. Okay? And HK converges to H infinity, that is 9. Okay? And this magic appears, and I will explain it why, is that although we are paying the price of always divided by this, at each step we have the square. So the square, so although the constants deteriorate quite rapidly, the square allows us to be very fast. Okay? I don't want to discuss this here because that's for another video, but I just wanted to show what are some basic ideas that happens in these KAM schemes. As always, I will put in the description below the Rootman paper in this case, and also the paper where you can follow this construction. Okay, there's a lot of papers, a lot of books, but one of the papers. Okay, thank you very much.